Alright, here go my Lagrangian mechanics video reassessment. I chose to do question number 2 from the test because I couldn't really find a good homework problem from the book. So I just chose to do question number 2 from the test to kind of show that I clearly understand basically what's going on with Lagrangian mechanics. Alright, so the question read, here's an Atwood machine. Use Lagrangian mechanics to find an equation of motion for the system. Assume the pulley is massless. Alright, so my first approach to the question is, how many degrees of freedom does the system have? And, the system has 2 initial degrees of freedom, which is y1 and y2. But therefore, if we come up with the equation of constraint for the system, which is y1 plus y2 is equal to a constant. So therefore, now we can get that down to really we got 1 degree of freedom for the system. Okay, so basically I start off by finding Lagrangian. That's step number 1. You find Lagrangian by finding the kinetic energy and the potential energy and subtracting. So right here I have to go through the motion of finding the kinetic energy. So therefore we know the formula for kinetic energy is 1/2 mv squared. So therefore in this case it'll be 1/2 m1 times y1 dot squared plus 1/2 m2 y2 dot squared, because those are just the derivative of the position, which gives me the velocity. So here we go. But see, right here we have a problem because we don't want this y2 dot squared. We only want one variable, because if we had 2 variables, saying basically we got 2 degrees of freedom, then therefore we'll have 2 equations of motion, and that would just make our problem more difficult than it has to be. So therefore we could take out this y2 dot squared and replace it, as I showed here. Y2 is equal to c minus y1, which is a constant minus y1. So therefore y2 dot is equal to the derivative of c minus y1. C is just a constant, so therefore y2 dot is equal to negative y1 dot, because we take the derivative of y1. Alright, so therefore we replace this y2 by negative y1 dot squared. Once you square it, it becomes positive, so therefore we got our equation for the kinetic energy is 1/2 m1 plus m2 times y1 dot squared. And we can change that to just y if we wanted to. Okay, next we find the potential energy, which is just U is equal to mgh, but see, we have to add the potential energy of each of these 2 masses together. So therefore U is equal to m1g times y1 plus m2g times y2. But like we said, we don't want 2 variables. We want to keep it at 1 variable. So therefore we take out this y2, because we said earlier in our equation of constraint that y2 is equal to a constant minus y1. So therefore our final equation for our potential energy is going to be m1g y1 plus m2g c minus y1. So therefore we move on to the Lagrangian, which is just subtracting these 2. So therefore we got L, our Lagrangian is equal to 1/2 m1 plus m2 times y1 dot squared minus m1g y1 plus m2g c minus y1. So next we add in our Euler-Lagrangian equation in order to come up with the equation of motion. So okay, so that's what I'm doing here. Our Euler-Lagrangian equation is the partial of the Lagrangian with respect to y minus ddt of the partial of the Lagrangian with respect to y dot is equal to 0. And like you said, we don't have to show the proof for that. We just have to know that it's true. So all right, here we go. So our Lagrangian, here we go. I rewrote our Lagrangian. And then so I started off with saying what's the partial of L with respect to y, which is basically just look at this part right here. What's the partial of this with respect to y? And we come out with negative m1g, because we take the derivative with respect to y, we get negative m1g, and then plus m2g, because here c is a constant, so we don't have to pay that no mind. And if we take the derivative with respect to y1, once again we get m2g. So yeah. And then so next I take the partial of the Lagrangian with respect to y dot. I get here, we get m1 plus m2 is y1 dot, and I just get that from here. Take the derivative of y1 dot squared, you get 2, that's going to cancel out, turn into 1, you get m1 plus m2 times y1 dot. And if you take the derivative of the partial of the Lagrangian with respect to y dot, you get m1 plus m2 equals y double dot, which is just the acceleration. And then here, this is basically just some algebra to get to single dot, y double dot, because that's our equation of motion. And this is what I end up with. All right, and that's it.